Okay, we've already started looking at the Gompertz mortality model. I'm going to summarize it and give you an example. I've already given you one example. I'm going to give you a more interesting example. So I looked it up. Gompertz originally wrote this thing in 1825. It applies to adults only roughly from their middle age, from age 35 or 40 on up to age 85 or 90 or so. What happens after age 85 or 90 is an open question. The question is, does mortality after that age plateau? Does it continue to look linear in the logs, or does it accelerate even faster? There's a lot of debate about what happens at the oldest old ages. But between these ages, like 35 or 40 and 85 and 90, log linearity in the mortality rate seems sort of okay. So let's remind ourselves, formerly the Gompertz model is mu of x, that's the hazard, is equal to some parameter alpha times e to the beta x, where x is age. So that is what we mean by log mortality is linear with age. So if we take the logs of both sides of that equation, we get the log of the hazard, the log of mu of x, equals the log of alpha plus beta times x. So now I'm going to suggest that you go to the Human Mortality Database, that's hmd.org, and you choose a country with a long series of cohort life tables. I chose Sweden. That was the longest series of cohort life tables, but you can choose any other country that they have in the Human Mortality Database. And then you download some life tables for each decade or whatever the interval is that you're interested in. And using the NMXs, the mortality rates from those life tables for ages 35 to 40 up to 80, 85, whatever, you can try to calculate what the log alpha and beta would be for several life tables. And now, what do you think you would get? Well, here's what I got. This is for Sweden. I'm going to move this up a little bit. Let's move this. Oops. I will do that later. So this is Sweden. And I have now calculated, based on the Gompertz model, log alpha and beta. And here are the years. I started at 1750, 1760, 1770, 80, 90, 1800, and then you see 1810, 20, 30, 40, 50, 60, 70, 80, 90, 1900, and 1910. So it's only in the first couple of years, first couple of decades, do you see it kind of swiggle around. But then after that, that's pretty amazing. That's pretty impressive. So even with this extraordinarily simple two-parameter mortality model, now it only applies to adults. We're ignoring children and young adulthood. Still, for adults, for a two-parameter model that was developed in 1825, that is 200 years ago, I would argue that's pretty good. And you could look at this as a time series and then make a projection about what would happen in 1920 and 1930 and so on. This turns out to be very closely related to the Lee Carter modeled mortality projection model. I may not get a chance to talk much about that, but if you understand this, then you are going to be close to understanding the Lee Carter model. It has a structure for the mortality rates. It looks for a way to parameterize them and then estimate them, and then projects those rates, those parameters, sorry, not the rates. It projects the parameters over time, and then it reverses the model in order to get new mortality rates projected into the future. So now I think an interim step is to talk about something called the Brass-Logit, relational logit life tables. Let me pause for a moment. Okay. So let's talk about the Brass relational logit model life table system. Now, Bill Brass was a demographer who worked at the London School of Tropical Medicine, and he specialized in Africa. And he had a problem, and his problem was that at the time when he was working, which was the mid-1970s, there were not very many reliable life tables that he could use to model the mortality experience in Africa, in the parts of Africa he was working in. So he had an idea which is actually quite close to the thing that we do now with Bayesian estimation, which is, his idea was, if he could find a good and reliable life table from somewhere close by in either distance or in time, then maybe he could use that as a standard or a basis, and then find a way to modify it in a parameterized, regular parameterized way, to create a whole new set of model life tables for the place that he was interested in. So we do this now where we try and use information from nearby states or countries or counties or cities and try to look at across time and smooth things out and try and project to find information which applies to a place for which we don't have data. So Brass started off, and he was familiar with the life table functions, and what he did was he decided that he would try to build this model life tables based on the LX curve. Now, let's remind ourselves that the survivorship curve looks, I guess in his area, it would have a steep little drop in the first couple of years because of infant and child mortality, and then it might decline like this, and then after you get to some older age, it goes down. So this was a typical LX shape. And one of the things that we've mentioned before about the LX curve, which is not true about many of the other columns of the life table, is that it is monotonic. LX is monotonic. and here is a true fact, things which are monotonic are easier to model than things which go up and down. So things which either look like this or things that look like this are easier to model than things that look like, say, this, or worse, maybe things that look like that. So Bill Brass had this idea, and he figured that it's easier to model based on a monotonic function, so he chose the Lx. And what was Bill's idea? Bill's idea was, can he find some function of the Lx curve which, when you add a parameter and you multiply it by something, you twist it and you move it up and down, can you modify it and then create a brand new set of life tables? So his idea was, let me see if I can write it down. Suppose he had some standard life table that he would call his standard. His idea was, can I find some transformation of this? So he wants to find some functional transformation of that. And then what he wants to do is he'd like to modify this and do something to it to create a new family. So what he wanted to do was to find something that he could multiply this by and add something to it, and that would give him a new family of LXs. And then he would untransform it. If this were true, then he would undo that transform, and so Lx new would be the untransformed version of alpha plus beta, the transformed version of his standard. So this was the idea. You find some transformation f. You multiply it by something, you add something, and then you untransform it and see whether that gives you something that looks reasonable for a new set of LXs. So Bill Brass tried many different possible forms for this function, this transformation function, f. And eventually he settled on something that looked like f of this L of x. He decided this was the log of L of x divided by 1 minus L of x. Now, L of x is our probability of surviving up to age x, so, and 1 minus L of x is the probability of dying before age x. So the ratio L of x to 1 minus L of x are called the log, if that's the odds of surviving to age x. And so this is the log odds, the log of the odds of surviving to x. And this is a very common function in mathematics, and it's the log of the odds of something. So that's called the logit. So it turns out that Bill Brass settled on the logit of L of x, and that's why this thing is called the Brass Relational Logit Model Life Table System. he takes the logit of L of x, he finds a brand new family based on alpha and beta. These are called relational models. So, it turns out that in many cases, if the new, I guess I should draw a quick picture. So if you were to draw a quick picture, the idea is, suppose you had the logit of our L of x standard over here, and we had the logit of our L of x nu over here. The alpha and beta mean that what we're suggesting is that there's some line, and this intercept at 0 is going to be alpha, and this slope is going to be beta. So the slope is beta, and the intercept is alpha, and then you untransform it, you untwist it. So it turns out that in most cases, alpha is close to 0 and beta is close to 1. I guess I should show you what happens. So suppose this was our original standard L of x. Let's see. What happens is that beta twists or pivots so it twists or pivots around this point here. So beta twists or pivots L of x. And it turns out that alpha in this system, so suppose now here's our L of x standard again, alpha would raise or lower. So it would look like this. It has to start here at the radix. It has to end at 0 there. So alpha will look like this. So alpha raises or lowers the Lx. So if you understand how this works, that gets you a long way to understanding how Lee-Carter models work. If I get some time later today, I will go through a little bit of the Lee-Carter models.